So what we are going to do now is we are going to learn oscillations. So oscillations is a 11th syllabus chapter, but this has quite a representation in different entrance exams. So first let us understand what is, you have already learnt earlier there is something called a circular motion, that when a body is moving in a uniform circle about a point. This is called circular motion. Suppose I take a point body and move it in a circle. Now we have also learnt about periodic motion, or we know that the sun revolves, the earth revolves around the sun, we know the moon revolves around the earth. So these are all examples of periodic motion. Periodic motion is basically any motion which repeats itself. In regular intervals of time. So if I take a body and make it move in a circle, so circular motion is an example of periodic motion. If I take a ball and allow it to bounce such that no energy is lost, so it will keep bouncing, that is also periodic motion. The movement of the satellites, the movement of planets, these are all examples of periodic motion. The movement of a pendulum is also an example of periodic motion. So if you take a simple pendulum and then you shift it a little that side and then leave it, you see that the pendulum oscillates about the mean position. So this is also periodic motion. So these are all examples of periodic motion, and these constitute a category of motion where the body repeats its motion in regular intervals of time. What we are now going to see, or what we are interested in, is something called as oscillations. Now there is a difference between periodic motion and oscillations. So the difference between periodic motion and oscillations is the fact that in oscillations the body has to undergo to and fro motion. That is to and fro motion about a mean position. Suppose you have the body here and you have the body here and it is moving about this. This is how the pendulum is moving. So it goes about its mean position. This is the mean position. So to and fro motion about the mean position is what is called as periodic motion. So for periodic motion there is a necessity that it should be to and fro motion. That is, there should be motion about a mean point. So this is the mean position of the body and the body is moving about this mean position. Then there is another requirement. You see, when the body is going in this direction, there is a tendency for the body to come back, to regain its original position. That is, some kind of elastic forces are required for to and fro motion. I won't call it elastic forces, I will call it as a restoring force. A restoring force is any force which tends to bring back the position of the body to its mean position. So now you see, when I take the pendulum and shift it this side, there is a force which acts on this side. That is, a component of tension is going to pull the body towards this side. Similarly, when I move the body onto this side, a component of tension will take the body to this side. So every time there is every time the body moves is a restoring force. So we can also say that motion in the presence of a restoring force is what is called as oscillations. Okay, now let's see if I can classify the other periodic motions into as oscillations or not. Now we said that the movement of a body in a circular path. Now whenever there is a circular path, there is a force which is acting towards the center. There is nothing called as a mean position. There is no to and fro position. So I can't classify circular motion as oscillatory motion. Similarly, we spoke of the bouncing of a ball. So now when a ball is, suppose this is the floor, and you take a ball and the ball is dropped down, it hits the ground and then it bounces back. Now you see, whether the ball is going downwards or upwards, gravity is only acting in the downward direction. That is, there is no restoring force. Restoring force, remember, changes its direction depending on how the body moves. If the body is moving left, the restoring force is to the right. If the body is moving to the right, the restoring force is to the left. So whenever the body bounces, there is no restoring force. So I cannot call this also as oscillatory motion. On the other hand, if I have, let's look at our pendulum, the example of the pendulum. Suppose I take my pendulum and then the pendulum was oscillating. When the pendulum moved towards this side, the restoring force was in this direction. When the pendulum moved to the other side, the force was again in the opposite direction. So whenever there is a force opposing motion, we will say that the motion is oscillatory motion. Okay, now in oscillatory motion, we can classify motion as simple harmonic and non-simple harmonic. Say for example, if I take a stone, or if I take a stone and say, suppose I hit it on a metal, I take a wooden hammer and bang it on the metal surface oscillates. Yeah, it moves to and fro. Now can I call that motion as a simple harmonic? No, it is oscillatory motion, but not all motion is simple harmonic. Only those cases of oscillatory motion where there is no loss of energy. There is no loss of energy and the body continuously oscillates. Once set into oscillation, the body continuously oscillates. I will call that as simple harmonic. Other than that, it could be called as damped harmonic motion. Okay, damped harmonic motion. Damped means when there is a loss of energy, and this loss of energy results in the body ultimately coming to rest. Okay, so what we have understood so far is, we have understood what is circular motion, then we have understood what is periodic motion. Within periodic motion, we have understood what is oscillatory motion. Between the oscillatory motion, we have classified it as two: simple harmonic motion and damped harmonic motion. Mostly we have simple harmonic motion in our syllabus, so henceforth we will deal with simple harmonic motion. What simple harmonic motion says is, when a body moves or oscillates about its mean position in the presence of a restoring force. In the presence of a restoring force. Now restoring force, I have already explained. Restoring force restores the original position of the body. Now you see, initially the body was displaced to the left. Now to restore its position, the force should act along this direction. So that is a restoring force. So that Fx actually will be a negative force and it is directly proportional to displacement x. So whenever I have a case where a body is moving such that the restoring force is proportional to negative x, where x is the displacement from mean position. Displacement from mean position. In such cases, I can term the motion of the body as simple harmonic. Okay, so let's try to understand this once again. I am saying that f of x is proportional to negative x, or I am saying that the force, which is the function of x, is equal to minus k into x, or m into a plus kx is equal to 0. Understand that force is equal to mass into acceleration from Newton's second law. So if a body moves such that its equation of motion can be written, such that the net forces acting on the body could be written as ma plus kx is equal to 0, I can say that the body is in simple harmonic motion. Okay, so such a body is said to be in simple harmonic motion. Ma plus kx is equal to 0. Now, suppose I have my body here and then I'm moving the body this side. You see, this is the maximum displacement the body has from its mean position. This is what is called as the amplitude of the body, of the displacement or of the SHM. So amplitude is the maximum displacement from the mean position is what is called as the amplitude. So every time a body oscillates in one complete to and fro motion, the body goes this side, comes back, goes this side and comes back. So in one complete to and fro motion, it travels a distance equal to 4 amplitudes. Okay, the displacement is 0 because it starts from here, comes back here, but it has traveled a distance of 4 amplitudes. Okay, so this is the amplitude. Now the time, so we have understood a word called the amplitude. Then there is something else called as the time period. The time period, I have already told you that oscillatory motions are periodic motion. So the time period refers to the time taken for one complete to and fro motion. So the time taken for one complete to and fro motion, that is how much time the body takes to go from here to here, comes back, goes from here to here and comes back, that is called as one time period. Now the reciprocal of one time period, suppose a body takes let us say half a second for one complete oscillation. How many oscillations will it make in 1 second? It will make 2 oscillations in 1 second. So we have something called as the frequency. Frequency refers to the number of oscillations per second, and that is equal to 1 divided by t, the time period. So you have time period which is equal to the time taken for one complete oscillation, and then you have frequency which refers to the number of oscillations per second. So you have time period. Now this time period, like you see, later on we will learn that simple harmonic motion could also be related to circular motion, and especially uniform circular motion. So in uniform circular motion you have something called as the angular velocity. Omega is the angular velocity. So in the terms of omega, time period is equal to 2 pi by omega. Similarly, I have also something called as the we have already written that frequency is equal to 2 pi, frequency is equal to 1 upon time period. So from there I can say frequency is equal to omega by 2 pi. So from there I can say that omega is also equal to 2 pi into frequency. So there are two formulas I have for omega. Omega is equal to 2 pi into frequency, or it is 2 pi by time period. It is referred to as the angular velocity. Okay, so this leaves me with just one more constant, the value for k. K is a constant which is called the force constant. It comes up in springs. We have learnt F is equal to kx. So this k is called the force constant. It is the extension. In this case, it is the extension required. It's the force required per unit extension. Force for unit extension. In this case it is force for unit extension, but otherwise we will just call it a force constant. Okay, it's a constant that we are using. Why are we using that constant? We are saying that f is proportional to negative of x, so we are saying f is equal to minus k into x. This k is a constant. So I have ma plus kx is equal to 0. Now a is what? D squared x by dt squared. So that is a is equal to dv by dt plus kx. Now v is equal to dx by dt. So I can say it is equal to m d squared x by dt squared plus kx is equal to 0. So I have m d squared x by dt squared plus kx is equal to 0. So now this is the differential equation. This is the differential equation that represents that represents simple harmonic motion. So that is a differential equation that represents simple harmonic motion. The solution to this will give you the value of x, that is how does x change with time. Okay, so this is a differential equation and we'll try to solve it. Now what we are saying is m into d squared x by dt squared plus is equal to minus kx, or d squared x by dt squared is equal to minus k by omega into x.